My slides are visible, right? Okay. Okay, thank you. So, welcome you all to this NPTEL course, a study guide in organic retrosynthesis, problem solving approach. Course instructor of this course is Professor Samik Nanda from IIT Kharagpur, and I am Anirban, so one of the TA for this course. So, coming to before coming to details of this course, so like previous last week, I have shown you the Nobel Prize winners uh, before 1955. So I will show you the Nobel Prize winners in between 1955 to 1994 in synthesis. Okay, so Nobel Prize winner of 1955 was Sir Vincent du Vignard. So basically, due to his contribution on sulfur compounds, especially for the synthesis of polypeptide hormones. Then after 1955, 1963, so Ziegler and Natta. So all of you know they are well known in polymer chemistry. So Ziegler and Natta, so they won Nobel Prize in 1963 because of the discoveries in the field of chemistry and technology of high polymers. So, followed by R.B. Woodward, Professor R.B. Woodward, he won the Nobel Prize in 1965 due to the achievements in the art of organic synthesis. So, in my first week of lecture, I have shown about his works in the field of organic synthesis. So, he won the Nobel Prize in 1965 uh, due to his contribution in the art of organic synthesis. Now coming to the 1968, so Haragobindo Khorana, so he is an Indian origin. So he was born in British India in Punjab province. Then he moved to then he moved to USA, and he won a Nobel Prize in medicine. So because of his interpretations of genetic code and its function in protein synthesis. Now, in 1969, Sir Derek H.R. Barton and Ord Hassel, so they own a Nobel Prize in 1969. So Barton is known for radical chemistry. Now they own a Nobel Prize in 1969 because the development of the concept of conformations and its applications in chemistry. So they own the Nobel Prize in conformational studies. So now this Sir Vladimir Prelog and John W. Cornford, they won Nobel Prize in 1975. So due to the stereochemistry of organic molecules and reaction, and John Cornford, he won a Nobel Prize because of his contribution in the field of enzyme catalyzed reaction, stereochemistry driven enzyme catalyzed reaction. So in 1979, Professor H.C. Brown and George Wittig, they shared the Nobel Prize. H.C. Brown because the development of boron compounds, and George Wittig, he won the Nobel Prize because of the developments of phosphorus related compounds. So all of we know Wittig reaction, so that is phosphorus based ylide. So Brown and Wittig, they shared the Nobel Prize in 1979. Now in 1981, Hoffman and Fukui, so they shared the Nobel Prize for the development of theories concerning the course of chemical reactions. And in 1984, Bruce Merrifield, so he won a Nobel Prize in the development of methodology for chemical synthesis on a solid state matrix. So followed by in 1987, so Lay and Pedersen, so they shared a Nobel Prize in 1987 due to the development and use of the molecules with structure specific interactions of high selectivity. Now 1990, Professor E.J. Kore, already I have discussed his contribution in organic synthesis in my second week. So he won the Nobel Prize in 1990 due to the development of theory and methodology of organic synthesis. And coming to 1994, George J. Ola, so he is known in carbocation chemistry, and due to his contributions in carbocation chemistry, he won a Nobel Prize of, in 1994. So you can see how many people they got Nobel Prize from synthesis background, not only synthesis like concept and theoretical background also they have won a Nobel Prize. So just a minute. Yeah. So you can see many people won the Nobel Prize in between. Like last week, I have shown from 90s to 1955, and this week I show you this Nobel Prize winners of 1955 to 1944. So this you should remember because this has highly impact in synthesis. Okay, so coming to the retrosynthesis, our topic. So already I have discussed these syntones and synthetic equivalents in my last two week lectures. So so just I have just you can see uh, so how we can get the syntones and synthetic equivalents of donor syntone and acceptor syntone. Accordingly, we can use these syntones and synthetic equivalent in our forward synthesis. Okay, so I will not go into the details about these syntones and synthetic equivalents because I have already discussed. So coming to directly into the problem, this is the molecule known as tropinone. Okay, and this tropinone was synthesized by uh, Professor Robinson in 1917. So as you can see, this is the paper in this is Royal Society of Chemistry journal. So he has published this synthesis of this tropinone in this journal. So now, yeah, now we'll devise a uh, retrosynthetic analysis or retrosynthetic path for this molecule tropinone. Okay, so you can see this molecule is happening in nitrogen functional group and a carbonyl functional group. Okay, so how we can get a retrosynthetic analysis? So basically this is the alpha carbon, like if we so compared to this carbonyl carbon, so this is the alpha carbon and this is the beta carbon, right? So similarly here, this side it is alpha carbon and this is beta carbon. Now if you see the functionality, so this nitrogen, this tertiary amine, it is connected to the beta carbon to the carbonyl group. So we can think about this retrosynthetic disconnection. Okay, now, because alpha beta unsaturated compounds or carbonyl compounds are electrophilic at beta center, so we can think about 1,4 addition of this methylamine to the unsaturated carbonyl compounds, right? So now, so this molecule can be redrawn as this molecule. So now you can get a better visualization. Okay, so this is alpha carbon, this is beta carbon, and this is alpha carbon and this is the beta carbon, right? So we got a better visualization from this by redrawing this molecule in this fashion. Okay, so now you can easily think about this 1,4 addition. Okay, so we can think about this C and beyond disconnection. So coming to next, so this is the retrosynthesis. So we can add this methylamine into 1,4 fashion to this one alpha beta unsaturated this cyclic carbonyl compound, right? And this compound, how we can get? So this compound we can get via, so this is the alpha beta unsaturated carbonyl compound. So if we do condensation reaction, okay, so by doing this CC bond disconnection, okay, CC double bond disconnection, so we can easily get this molecule. So condensation between this carbon, so this carbon and this aldehyde, right? So similarly, for the bottom part, this carbonyl and this carbon. Okay, if we do condensation reaction, we can easily get this alpha beta unsaturated carbonyl compound. Now, so this is the retrosynthesis, right? So how we can do how we can think about forward synthesis, right? So for forward synthesis, so we have taken this aldehyde dialdehyde, and this is so beta carboxylic acid, okay, beta keto dicarboxylic acid. Now if we heat these two compounds in pyridine, and if we do reflux, so what will happen? So this is the condensation reaction. So this this unsaturated compound will form again for the second condensation. So this condensation will happen, okay. So base will abstract proton from here, and it will adds to this aldehyde, and it will give the corresponding unsaturated carbonyl group, right? So you will get this type of compound, right? Now if we add methylamine, so in into 1,4 fashion, so we'll get this compound, right? So this is the Michael addition. So this is nothing but Michael addition. All of you know this 1,4 addition is known as a Michael addition, right? So this Michael addition of one methylamine, you can get this compound. Now CO2 elimination. So this is the beta keto acid. Okay. So this is the alpha carbon, and this is the beta carbon. Okay. So similarly, this is alpha prime, and this is the beta prime, right? So this beta keto acid, you can provide heat. So this is the symbol of heat, and you can easily get the removal of carbon dioxide. So so beta keto acid you can generate easily the carbonyl compound, right? So this is the tropinone. Now one name reaction involved in this transformation. So this condensation reaction, okay, condensation reaction between this aldehyde and this beta keto acid. So mm, this is the known reaction known as Doebner condensation reaction. So condensation reaction between ester, if it is ester and this is aldehyde, then it is called novenazole condensation. Now if it is having acid instead of ester, that time we will call it as Doebner condensation reaction. Okay, so this is the Doebner condensation reaction mechanism I will show you. So in Doebner condensation reaction, we have to use pyridine. Okay, both as a solvent and as a base. Okay, so what will happen? First, pyridine will abstract proton from here, right? So this is the more acidic proton here. So first enolate will form. Okay, so this is the enolate, right? Enolate. So this is the enolate. Now after formation of enolate, what will happen? Just a minute. Okay, so after formation of this enolate, so what will happen? So this enolate will adds to this aldehyde, right? So first this enolate will, so this anion, oxygen anion will form here, and this C bond will will move to this aldehyde. So we'll add to this aldehyde, and this will give this beta hydroxy. This is alpha carbon, this is alpha carbon, and this is beta carbon, right? So beta hydroxy uh, compound, right? So similarly again, this side enolate will form, and it will add to this aldehyde. So similarly if we treat with base, so enolate will form, this is the enolate, and now this enolate will add to this aldehyde, right? So enolate, so this will fall, this will move to here, and this will give to the corresponding beta. So again this is the beta, and this is alpha. So beta hydroxy ketone, okay. So now what will happen? So now in presence of pyridine and heat, so this reaction is under reflux condition, so you are providing heat. So what will happen? So pyridine will take So this is the carboxylic acid. So pyridine will take this proton, right? So if this is the pyridine. So pyridine will take this proton and decarboxylation will happen. So this OH bond will break, and here double bond will generate, and this will come, and this will come back again, and this CC bond will break. Okay, this CC bond will break, and this hydroxy group will remove. Okay, so basically removal of minus CO2 and elimination of this water, you will get, so minus CO2 and dehydration. Okay, minus water, you will get this alpha beta unsaturated, this carbonyl compound. Okay, so similarly this side also same, in similar way you will get this alpha beta unsaturated ketone compound. So this is the diagonal condensation mechanism. Okay, now coming to the next retrosynthetic analysis. So this is the compound. Okay, so if you see this molecule clearly, so what it is having, so basically it is having this ester group. This is the ester group, right? And this is the carbonyl group, and this is the olefin, right? So this, if you see this ester, so this is the alpha, and this is the beta. Okay, so this is the beta keto ester. Okay, so this beta keto ester, how we can get, so I last week also I discussed. So anyway, so this will also I show you how we can get this beta keto ester. So if we think about this CC1 disconnection, okay, this CC1 disconnection, so this CC1 disconnection, if we think, then what are the syntones we can have. So if this carbonyl carbon is having positive charge, then this alpha carbon should have negative charge. Okay, so this alpha carbon negative charge we can easily generate, and now this carbonyl carbon positive charge, how we can get. So now we can see the syntones. So this is the acceptor synton, right? Acceptor synton, and this is the donor synton. Now what will be the synthetic equivalent for this synton? So this is the synthetic equivalent. So from here we can easily generate the carbon, and from here we can easily, so this ester, so ester is electrophilic, right? So this, that means this carbon is positive. Okay, so this carbon is delta positive, so ester is electrophilic, so we can easily generate this acceptor synton from this ester, and donor synton from the corresponding ester, right? Now from where we can get this synthetic equivalent? So again, the synthetic equivalent we can generate from this CC1 disconnection. Okay, so this CC1 disconnection, if we do, if we can think about this CC1 disconnection, then what will be the synthetic equivalent? Sorry, syntones, right? First, so this CC1 disconnection mean, so this carbon and we can think, and this carbocation we can think. Okay, so this is the donor synton, right? So it can donate, so this is the donor. So this is the donor synton, and this is the acceptor synton. So this is the acceptor synton, right? So now this donor synton we can easily get from this compound, and acceptor synton, so we can get from this R halide compound. Okay, so because this can act as a electro, so this carbon is electrophilic now. Okay, delta positive. So this carbon is electrophilic now. So from these synthons we can easily get the corresponding synthetic equivalents, right? So now after this we will see how the forward synthesis, what will be the forward synthesis. Okay, so this forward synthesis, we have taken this synthetic equivalent for donor synton, right? So we can easily generate carbon and from here, because it is having this acidic proton, right? So basically, if we treat with base, so base is LDA. Already I discussed in last week what is LDA. LDA is lithium diisopropyl amide. Okay, so and we have I have explained how we can generate LDA in situ in lab. Okay, so this is the diisopropyl group and Li plus. Okay, Li plus and N minus. So this is the lithium diisopropyl amide known as LDA. Okay, so LDA is a bulky base. You can see it is bulky. So it can take this proton and it will generate the corresponding enolate, right? Corresponding lithium enolate. So this will be the lithium enolate, right? So this counter cation for this enolate will be lithium plus. Okay, so after generating this lithium enolate, so if we treat this lithium enolate with this compound, so basically what will happen? So this is the electrophile. Okay, so it is this, so gamma bromo compound. Okay, gamma bromo ester. So basically this enolate will fall here, and this will add to as a SN2 pathway, and it will generate the corresponding compound, right? So this is the SN2 reaction with this enolate and this halide compound, right? So we will get easily this compound. So this compound we can get. So now if you see, so this is having this ester, carboxylic ester, and this is having this one, two, three, four carbon ester. Okay, so now we have to cyclize it. Okay, so cyclize how we can get, how we can do. So now if you see, this is having two acidic proton, right? So alpha to this ester. So those two protons, methylene protons are acidic in nature. Now if we treat with base, okay, so base like some stronger base like sodium hydride or potassium hydride. So here we use sodium hydride in THF. THF is solvent, right? So tetrahydrofuran. And if we reflux this reaction mixture, what will happen? So this proton, right? So this enolate will generate. So this enolate will generate, and this will add to this ester. Okay, and this OAT will remove. Okay, so basically we will get one, two, three, four, five member ring, right? This is a one carbon, this is the second carbon, the third, similarly this is the fourth, and this is the fifth number carbon. Okay, so you will generate this five member ring. So this is the beta keto ester. Okay, so beta keto ester. So this reaction, the name of this reaction is known as Dickman condensation. So Dickman condensation, basically it is a condensation reaction between two ester. Okay, so to form a beta keto ester. So this is the alpha carbon and beta carbon. Okay, so this is the beta keto and ester. Okay, so sometimes you will have in your retrosynthesis some beta keto ester type of fragment. Okay, and if you see this beta keto ester in your target molecule, so you can easily think about Dickman condensation. Okay, so Dickman condensation you can easily think basically. So this alpha beta fragment, alpha beta CC1 disconnection you can think, and you can think about this carbanion and this carbocation, right? So this is, just a minute. Yeah. So so if we have beta keto ester in our compound, so we can easily think about this alpha and beta bond CC disconnection, and we can easily think about that this could be derived from this diester. Okay, and so the condensation reaction is it can be done by using sodium hydride or potassium hydride in reflux condition. Okay, so basically sodium hydride and potassium hydride, the pK value for those bases are like 35 to 37. Okay, and this acidic proton it can easily take, and it will adds to the carbonyl of ester, and it will remove. So you can easily get this beta keto ester, right? So now coming to the next problem. So next problem, if we see, so again this molecule. Okay, so this molecule you have to visualize fast. Okay, so what it is happening. So yeah, so if we visualize this molecule, what comes into your mind first. Okay, so it is having this olefin. So this olefin, and also it is having a carbonyl group and a ester. Now we have to see the relation between this ester and carbonyl group, right? So what is the relation? So relation, if you see, so this is, so if we ester, so this ester, so this is the alpha carbon and this is the beta carbon, right? So if you see, so this is again a beta keto ester, right? So again it is a beta keto ester. So beta keto ester. So already last slide we have discussed about beta keto ester, how we can easily generate this beta keto ester. So basically if we have beta keto ester in our compounds, so we can easily think about this alpha beta bond disconnection approach, right? And if we do this disconnection approach, so this is the right disconnection for this beta keto ester. And if we do this disconnection, what will be the synthetic synthon? Okay, so synthon will be, so this carbon we can think about, and this carbocation we can think about. Okay, so this carbon we can generally we can easily generate from this ester, because this alpha proton are acidic. If we treat this with base, we can easily generate this carboanion here. Now how, from where we can get this ester, sorry, this electrophilic acceptor synthon. So this is the acceptor synthon part. So from where we can get, if we have this ester, this side also ester, so we can easily generate this synthon. So what will be the synthetic equivalent? The synthetic equivalent is this. So this is the symmetric ester. Okay, so ch2 ester, ch2 ester. So so basically, so this carbon we can easily generate, and it adds to this, sorry, it adds to this electrophilic center, and we can easily generate this compound. Now from where we can get this symmetrical diester. So if we think, so this we can get from this symmetrical diol. Okay, so symmetrical diol, from where we can get this ester, symmetrical ester. Now coming to the forward synthesis, so mm, this is the retrosynthesis for this beta keto ester. So forward synthesis, so we will start from this symmetrical diol, this cyclic molecule. So first, this molecule, what we will do first? Yeah. So basically, this diol will make, will convert this diol to leaving group. So by treating with this diol with methyl chloride, triethylamine as a base, and DCM as a solvent. So methyl chloride is basically methane sulfonyl chloride. Okay, so SO2. So this is the SO2 methyl, and this is the leaving group chlorine. Okay, so this how this will happen first. This oxygen lone pair will adds to the sulfur, and this HCl bond will break. So now this triethylamine will take this proton. Okay, so basically in this mechanism you can get this O missile. Okay, so methane sulfonin chloride, if you treat in presence of triethylamine in DCM, you will get, we can easily convert this hydroxy group to leaving group. Okay, so this O missile is now, as it is, it will act as a leaving group. Okay, so that will act as a leaving group. That means, so this carbon will be delta positive now. Okay, similarly for down part, this carbon will show delta positive character. Okay, so after this formation of this dimethylate compound, we will do some SN2 reaction. So SN2 reaction between potassium cyanide. Okay, so potassium cyanide is a salt. So basically this cyanide, so this SN2 reaction will happen. Both side cyanide addition will happen, and you will get this cyanide dicyano compound. Okay, so from this diol to dicyano compound you get now. Now what is the next reaction? So next reaction is the conversion of the cyanide to acid. So this is the hydrolysis reaction. Okay, so in presence of KOH and ethylene glycol, if we reflux this reaction mixture, so we can easily get the hydrolysis of cyanide, and we can easily get this acid. For both acid we will get. So this is again the symmetrical acid. Now what is the next reaction? So S, so this acid we get, now we have to convert to acid to ester. Okay, so this is the acid to ester. So this acid to carboxylic acid to ester, how we can get? By treatment with ethanol in presence of catalytic amount of H2SO4. Okay, so this is a known reaction. Okay, so this reaction is known as Fischer esterification. Okay, so esterification between acid and alcohol in presence of catalytic amount of H2SO4 is known as Fischer esterification. Okay, so this esterification is known. So this is the Fischer esterification. Okay, so after getting this diester, so we have to do the Dickman condensation reaction. Okay, so to in order to get this beta keto ester, so we have to treat with sodium hydride or potassium hydride. So in THF, so basically, so this carbon will generate, and it will add to the carbon in carbon of this ester, and it will give this. So this, it will give this alpha beta. So this is the beta keto ester, right? So this reaction already we know okay, this is known as Dickman condensation reaction. Okay, so now this reaction is reported by Professor this Hitchcock in Journal of Organic Chemistry journal. So in ACS journal, American Chemical Society journal. So JOC in 1996 he reported this forward synthesis in this journal. Okay, so for better understanding you can visit this journal in order to get the detail about this forward synthesis. Okay, so now coming to the next slide. So next slide, this is an interesting example. Okay, so if you see this molecule, so you just visualize what it is having in the structure. Okay, so what are the functional groups present in this molecule? Can you visualize this molecule? So if you visualize this molecule, it is having this aromatic side part, also in carbonyl group and also an olefin group. Now the relationship between this olefin and carbonyl group is interesting because this is alpha and this is beta carbon. Okay, so this is the alpha beta unsaturated carbonyl compound. Okay, so this alpha beta unsaturated carbonyl compound, how we can get. So so many times we have discussed, also Professor Samignanda also discussed how we can get this alpha beta unsaturated compounds, okay, carbonyl compounds. So basically if we do aldol reaction, okay, so if we have, so if we think about this CC1 disconnection, so this carbonyl group and this side, okay, so aldol reaction between this carbonyl group and this carbonyl, so we can easily get this alpha beta unsaturated carbonyl compounds. Okay, so first aldol reaction followed by dehydration. So first beta hydroxy ketone will form, then dehydration. We can easily get this target molecule, right? Yeah. Now from where, now how we can get this? So this relationship you see, 1 2 3 4. So this alpha beta gamma delta, delta alpha, yeah, alpha beta gamma delta epsilon. So alpha epsilon carbonyl compounds, how we can get. So again we have to think about CC1 disconnection. So we can think about this CC1 disconnection, right? So if this CC1 disconnection we are thinking, so what will be the corresponding synthetic equivalence, right? So the synthetic equivalence, coming to synthetic equivalence. So before we have to see the syntones. Okay, so this is the donor synthone. So basically we can think about this carboanion and this carbocation, right? So this will be the donor synthone. So this is the donor synthone and this is the acceptor synthone, right? So now this donor synthone we can easily generate from this cyclo this compound, and acceptor synthone we have to think about this alpha beta unsaturated carbonyl ketone. Okay, so this will be the synthetic equivalence. Okay, so this will be the synthetic equivalent, right? So this is the synthetic equivalent. Now again we have to, so this synthetic equivalent for this acceptor synthone, so this is basically methyl vinyl and ketone. Okay, so MVK is a high MVK commercial name of this methyl vinyl ketone. So this side is methyl, this is vinyl, and this is ketone, so methyl vinyl ketone. Now this we will do retrosynthetic analysis. So basically if we think about this CC1 disconnection, okay, so this CC1 disconnection approach if we think, so basically we can think about this side, this acid chloride, right? So this CC1 disconnection approach, so this CC1 formation reaction, so this is very known in aromatic substitution reaction known as Friedel cap acylation reaction. So we all of we know what is the Friedel cap alkylation reactions and acylation reaction. So this cyclic compound we can easily get from this aromatic compound via with the help of Friedel cap acylation reaction. So this is the acyl chloride. So if we treat with this compound with any Lewis acid, okay, like aluminium chloride, aluminium trichloride, or any other Lewis acid, and heat it or reflux it, then we can get this cyclation reaction. Okay, so coming to, and this acid chloride from where we can get, so acid chloride we can get from this corresponding acid. Okay, just a minute. Yeah, so this acid chloride, so this acid chloride from where we can get, so we can get from the corresponding acid. Okay, so this is the carboxylic acid side chain. So this is the aromatic ring with having this carboxylic acid side chain, and if we treat this carboxylic acid with SOCl2, we can easily get this acid to acid chloride. So coming to the forward synthesis. So forward synthesis, what we will have, so we can have this carboxylic acid, right? So what we have to do next, we have to convert this carboxylic acid to acid chloride. So we can treat this acid with as SOCl2, and we can easily get this acid chloride, right? So what will be the next? Now next we have to do this cyclization. Okay, this CC1 cyclization. So if we do, how many member ring will form? This one, two, three, four, five, six. So six member ring will form now. Okay, so we have to do the Friedel cap acylation reaction in the presence of this aluminum trichloride. So we can get after the Friedel cap acylation reaction, we can easily get this compound. Okay, so this is a six member carbonyl compound. So now we have to install side chain from this side. Okay, so this side we have to install side chain. So just a minute again. Yeah, so this side, so after the Friedel cap acylation reaction, so this is the Friedel cap acylation reaction, you will get this carbonyl compound. Now we have to install the side chain in the right side. Okay, right hand side. So how we can install? So basically we have to treat this with base. Okay, so if we treat this with base sodium methoxide, so the pK value of sodium methoxide is about 17 16, right? 16 I guess. So the pK value, sorry, pK value of the sodium methoxide is uh, 15 to 16. Okay, so basically it will abstract the proton from this side. So it will abstract the proton, and enolate will form, and that enolate will adds to this alpha beta unsaturated carbonyl compound. No, so this is the methyl vinyl ketone. So Michael addition or 1,4 addition reaction will take place. Okay, so and we will get this side chain. So now we easily install this side chain with this carbonyl side fragment. So after that we have to do what are the what is our next target. So we have to do this allol reaction, right? So allol reaction in presence of this KO is ethanol and heat. So we'll do the allol reaction. We'll carry out the allol reaction. So first what we'll get? So first we'll get this beta hydroxy carbonyl compound, right? This is alpha carbon and beta carbon. So generally in allol reaction, we get this alpha beta hydroxy carbonyl compound, right? So after getting this beta hydroxy carbonyl group, if we reflux it, then dehydration will take place. So basically elimination of water. So and we can easily get this alpha beta unsaturated carbonyl compound. So now, so this is an interesting example of an annulation reaction. If you clearly observe this reaction, so first, so this step, so this step and this step. So this step, what is the reaction? What is the name reaction? Can anybody tell? So this to this conversion, what is the name reaction? Can anybody tell what is the name reaction? Okay, so this is basically 1,4 addition reaction, right? So 1,4 addition reaction, also known as a Michael addition reaction. Okay, so basically Michael addition of this enolate to this methyl vinyl ketone. Okay, so this reaction, Michael addition reaction, is taking place in the first step. followed by what is the reaction. So now after Michael addition you have this diketone compound, right? So diketone compound, so if you treat the exact like proper reagent like potassium hydroxide base and solvent and heating condition, so you will get first aldol condensation through this carbon, right? Through this carbon aldol condensation, then dehydration. So this is basically first step is Michael and second step is aldol, right? So this is, so this is the aldol and this is the 1,4 addition. So this is the 1,4 addition, right? So this 1,4 addition followed by aldol, and if you see also you can, you got a ring, okay? So you got a fused ring here, okay? So this is why it is called annulation reaction, and the name is Robinson annulation reaction, okay? So already we have discussed this many before also. So this is the Robinson annulation reaction. So Robinson annulation reaction mean it includes Michael addition reaction followed by aldol condensation reaction. Okay, so this is an combination of two reaction, two non reaction. One is Michael reaction, another is aldol reaction. So first Michael reaction is happening, then aldol reaction is happening. Also in this conversation, in this conversion, one ring is also forming. That is why it is called Robinson annulation reaction. So this annulation mean formation of ring. Okay, so annulation mean, if you heard anytime annulation means you will create any rings. Okay, so rings formation reaction. Okay, so in this reaction, if you see, so so this is also an example of, so multi-step reaction known as tandem reaction. Okay, tandem reactions or cascade reactions. Okay, tandem reaction and cascade reaction. Or last week also I have discussed. Tandem mean or cascade mean in one pot multi-step reaction will happen. Okay, basically if you treat any compound with suitable reagents and reaction conditions, then whatever functional group will form in the first reaction, that will trigger the next reaction. Okay, in same condition, 2 3 4 5 multiple step will happen. Okay, so that time we call those reactions as tandem reaction or cascade reaction. Okay, so Robinson annulation reaction also known as tandem reaction or cascade reaction. So so this is you can see in Robinson annulation two reaction is happening. One is Michael and aldol reaction. So in same pot, so you can do this two name reaction in same pot. That is why it is also known as tandem reaction. Okay, so I guess you get an idea about tandem or cascade reaction. Also get an idea of Robinson annulation reaction. Also what is annulation reaction? Annulation mean formation of ring. Okay, so after this we'll move to the next problem. Okay, so if you, so you just visualize this molecule. What are the functional group you are having in this molecule? So this visualization is extremely important in order to do the correct retrosynthetic analysis. Okay, so if you just visualize this molecule, just I'm giving you just 1 minute. So you just visualize this molecule, what are the functional groups it has, and how we can think the retrosynthetic plant for this molecule. Just think for 1 minute. Okay, so after visualization, if you visualize this molecule, like thing, you can say it is having a lactone, right? So this is the cyclic ester. Also, you can call it lactone, right? Also, it is having a primary alcohol. Okay, this CH2 is primary alcohol, and also it is a bicyclic compound. Okay, the 6 fused bicyclic compound, where the ring junctions are C stereochemistry. Okay, so ring junction means this carbon and this carbon. If you see the ring junction, so this both ring junction are cis. Okay, so that means you have an ester, you have an primary alcohol. So how we can think about the retrosynthetic analysis? So this ester we can easily think about this lactone, this CC1 disconnection. Okay, so that means, so this CC1 disconnection, right? So this CC1 basically, so this carbon and this carbon bond will form. Sorry, this carbon and this oxygen bond will form. So this is ester formation reaction. Now, what is the next step? So next step is basically the functional group interconversion. Okay, FGI. So if you have the ester, so you are having this ester here, right? So if you do reduction of this ester, then you can get this primary alcohol, right? So this is the functional group interconversion. Now, what is the next? So next, how we can get this acid and ester and this alcohol? So if we have this olefin, right? If we have this olefin, enol TMS, basically this is enol TMS. And if we do this CC1 disconnection, okay, so this CC1 disconnection, enol TMS, or this olefin, we can think about ozonolysis. Okay, if we think about ozonolysis, so this side will get aldehyde, right? CHO. This side will get this aldehyde in this carbon, and this side will have this acid, right? So this acid we are having, and this aldehyde, if you see, so this aldehyde, this stereochemistry, if you see here, this is alpha, right? This alpha bond. Here also alpha bond, and if you do reduction of this aldehyde, you can get this alpha primary alcohol, right? So very interesting. So now how, from where we can get this? Now from where we can get this enol TMS? Okay, so enol TMS we can easily get from this carbonyl compound, right? So if we treat this carbonyl compound with base and then TMS chloride, then we can easily get enol TMS, right? So this is not that much complex, right? Yeah, yeah. So in forward synthesis will start from this carbonyl compound. So this carbonyl compound, so this is trans junction transfused carbonyl compound. S- so basically this is your starting material, right? So what we have to do first, enol TMS we have to introduce. So how we can do introduce this enol TMS? So basically if we treat this enol carbonyl compound with triethylamine and TMS chloride in DMF, we can easily generate this enol TMS, right? First enolate will form. So enolate will form, and then enol to enol TMS, right? So enolate will attack to TMS chloride and it will give this OTMS, right? So enolate have two nucleophilic center. Okay, so if we just a minute. So this is the suppose enolate. So enolate is having this R. This is R. Okay. So enolate having two nucleophilic center. So this O minus can act as a nucleophile, and this carbon also is a nucleophile. Okay. Now this in between oxygen and carbon, which will attack to this, which will add to this TMS chloride. Okay. So this oxygen minus and the C minus. So in between O minus and C minus, so O minus is hard center. Okay, so we have to think about hard soft acid base concept. Okay, so this is the hard nucleophile and this center is soft nucleophile. Okay, so this is the soft center. Now you have to think about the electrophile also. This is TMS chloride. TMS chloride is basically silyl base reagent, right? So silicon chlorine bond is having. Now the silicon is hard in nature. Okay, so as the silicon is hard, so this enolate will acts as a, like, enolate will um, adds through oxygen center. Okay, because this hard matching is happening here. Okay, so this O minus will adds to the silicon, and you will get this enol TMS, right? So you can get, so you generate this enol TMS now. So you got an idea of about this oxygen nucleophilic center and C nucleophilic center. What will, so which will acts as a nucleophile. It depends on the electrophile. Okay, so now this enol TMS, after that we have to do the ozonolysis. So ozonolysis basically, so first this ozonide will form, and then you will get this carbonyl group here and this carbonyl group here. This carbonyl mean, so here you will get the basically CH2CHO. Okay, so this ozonolysis between this CC double one, so you will get CH2CHO. So this aldehyde, and here you will get this carboxylic acid. Okay, already one alcohol is having, and here this carbonyl group. So this aldehyde and carboxylic acid, you get this. So after that, what do you have to do? We have to do this reduction of this aldehyde. Okay, so basically how we can do, if we treat this aldehyde with sodium borohydride in methanol, we can easily get this primary alcohol. Now the stereochemistry, if you see, this primary aldehyde stereochemistry is alpha. Okay, so this is the alpha, so this is the alpha and this is the beta stereochemistry. Okay, here alpha beta we are talking in terms of stereochemistry. So this alpha is aldehyde and beta is ester. Okay, so now after reduction, the same stereochemistry contains, right? Just a minute. Yeah. So this, after getting this aldehyde, sorry, this alcohol from this aldehyde, so the next is we have to do the reduction of this ester. This reduction of this ester in presence of acid, we can easily do the selective reduction. Basically, chemoselective reduction of this ester in presence of acid we can do by using this Barch reduction condition. Okay, so sodium liquid ammonia in ethanol. So this is the Barch reduction condition. So in Barch reduction condition, we can easily do the selective chemoselective reduction of this ester in presence of acid. So sodium will act as a single electron donor, and it will adds to the carbonyl carbon of this ester. Okay, so the single electron will adds to this carbonyl carbon. Okay, and then so reduction will happen, and you will get this primary alcohol, another primary alcohol. Now what will be the next? The next is, now you are having this side, the bottom part is having this carboxylic acid. Okay, and often top side it is having two primary alcohol, this This is the primary alcohol, this is the primary alcohol. Now if you see this primary alcohol, so this primary alcohol is in cis, so this and this carboxylic acid both are cis. Okay, so both are cis. Okay, so this and this are cis, right? And this carboxylic acid and this alcohol, that are trans. Okay, now if we want to do esterification reaction between this carboxylic acid and these alcohols, so which alcohol will form ester? Okay, so you can easily get an idea because of the C stereochemistry of this alcohol and this carboxylic acid. So this alcohol will react to this acid and it will form the ester. Okay, so basically if you treat this molecule in catalytic amount of H plus, so and then water addition followed by work up, you can easily get this uh, delta lactone, right? This six member lactone or delta lactone. So this known name reaction, it is already I discussed 2 3 slides back. So the name reaction between this esterification between this alcohol and acid is also known as Fischer esterification reaction. Okay, so in presence of catalytic amount of H plus, if esterification happen between acid and alcohol, so we can call it as Fischer esterification reaction. Okay, so this is the target molecule we get. Okay, after Fischer esterification we got the target molecule. And also Professor Heathcock in this JOC paper in 1976, he published this work in JOC paper. So this JOC is an ACS journal, right? American Chemical Society journal, Journal of Organic Chemistry journal. Okay, so this Heathcock, Professor Heathcock, he published this work in this journal. Okay, you can also revisit to get detail about this work. Okay, yeah. Now coming to the next problem. So next problem, if you see this molecule, yeah, if you see this molecule closely, so it is having an carbonyl group, also an beta hydroxy group. Beta mean stereochemistry. Stereochemistry is beta. Beta mean above, right? So beta hydroxy group and this 6,5 bicyclic compound. So this 6,5 fused bicyclic compound having trans ring junction. Okay, so this carbon and this carbon, the ring junction is trans, right? So this trans fused 6,5 ring junction also having this carbonyl group here and also beta hydroxy group at this center. Okay, so how we can think about, so first we can think about some functional group interconversion. Okay, so FGI. So if we think about some FGI, just a minute. So if we think about FGI, so what will be the corresponding functional group interconversion? So basically reduction of this carbonyl to alcohol, also protection, removal of protected group. So it is ethylene glycol protection of this carbonyl group. So if we deprotect this ethylene glycol, you can get easily this carbonyl group. Okay, so this is the functional group interconversion. Now what is the next? So next is, if we think about reduction of this alpha beta, so this is alpha beta unsaturated carbonyl compound. Okay, if we think about this reduction of this alpha beta unsaturated carbonyl compound, we can get this compound, right? So now how we can get alpha beta unsaturated carbonyl compound. So already in last problem we have discussed how we can get this alpha beta unsaturated carbonyl compound, right? We have already discussed how we can get. So basically if we think about this CC bond disconnection, okay, so basically from aldol reaction we can get beta hydroxy alcohol, and then dehydration we can get alpha beta unsaturated carbonyl compound, right? So basically if we have this carbonyl group and this carbonyl group, so aldol reaction between this and this, okay, so we can easily get this alpha beta unsaturated carbonyl compound. Fast cellular reaction followed by dehydration of beta hydroxy alcohol. We can get this. Okay. Now from where we can get this compound? So now we can think about. So this is the 1,3 dicarbonyl compound. So this 1, 2, and 3. So this 1,3 dicarbonyl compound. So this methylene carbon used to be acidic, right? So we can easily think about this CC1 disconnection, right? This CC1 disconnection. Sorry, this molecule and this molecule are same. Yeah, this CC1 disconnection. So this molecule and this molecule are same. I have redrawn. Okay, so this CC1 disconnection, if we think, so basically this is alpha and beta carbon. So beta carbocation mean we can easily get from alpha beta unsaturated carbonyl compound. So this is methyl vinyl ketone. Okay, so the methyl and vinyl. So this methyl vinyl ketone, and easily we can generate carbon and here, and we can add to this methyl vinyl ketone as 1,4 fashion or Michael addition fashion. We can easily get this compound, right? Now from where we can get this molecule? Methyl vinyl ketone is commercially available, no problem. So from here we can get this 1,3 dicarbonyl compound with this side chain. Okay, so we can think about this CC1 disconnection. Okay, again this carbon and we can easily generate from the 1,3 diketone. So this carbon and we can easily generate from 1,3 diketone and this delta positive. So this will act as a electrophile, and this will act as a nucleophile after treatment with base. Enolate will from this 1,3 diketone, and then this enolate will adds to this ethyl iodide, right? So we can easily get this compound, right? So the synthetic equivalence for this is this ethyl iodide and this 1,3 dicarbonyl compound. Now coming to the forward synthesis. Yeah, so forward synthesis will start from this 1,3 diketone compound, right? So so if we are having this 1,3 diketone compound, so the pK value, so pK value, the I will show you. I will write the pK value. So these are the most acidic compound, right? So pK value you should know, because what type of base you have to use in your forward synthesis, you can easily get an idea by knowing the pK value. PK value is around, I guess, 9, 10 to 11, right? Exactly, I forgot. So pK value is 10 to 11, I guess. Yeah, 9, 10, or 11, I exactly forgot, but around in this range the pK value of this 1,3 dicarbonyl compounds. So basically we have to take proton from this, so we can treat with K2CO3, right? So K2CO3 is having pK value. The pK value of K2CO3 is 17. So you have to use the base which is having more pK value, okay, rather than the acidic proton. Okay, then only base will abstract proton from here. So this K2CH3 will abstract proton from here and it will generate the enolate. Now if you add enolate to this electrophile ethyl iodide, you can easily get this compound, right? And here n-butyl ammonium bromide is used. So this will play and role as a phase transfer catalyst. Okay, so this will act as a phase PTC, phase phase transfer catalyst. Okay, all of you know the role of phase transfer catalyst in SN2 reactions. So basically, it will enhance the reactivity of this enolate, right? So PTC, you can read details in Google, or you can some textbook, you will get what is the role of PTC. I guess all of you know the role of PTC. So it will enhance the reactivity, the nucleophilicity of this enolate, right? So now after this formation of the CC bond, so what we have to do? We have to generate again enolate here, okay? And we have to add that enolate to methyl vinyl ketone, okay? So first this Michael addition. So this we will add here. Okay, so this beta carbon is electrophilic. So this enolate first sodium methoxide. Sodium methoxide, the pK value is 15, right? The pK value of sodium methoxide is 15. So this will abstract proton from here, and then this enolate will add to this methyl vinyl ketone, and you will get this carbonyl compound, right? Very simple. Now what is the next? Next is very interesting reaction. So this is the aldol reaction, sorry, Michael addition reaction. Okay, so 1,4 addition reaction, 1,4 addition reaction or Michael addition reaction, right? So 1,4 addition reaction or Michael addition reaction. Now followed by aldol condensation reaction. So aldol reaction or aldol condensation reaction. First it will, so this enolate will form and it will adds to this carbonyl compound, right? And it will generate first beta hydroxy alcohol, right? So this is the beta hydroxy alcohol. So alpha carbon and beta carbon, right? So first beta hydroxy alcohol will form, and then in reflux condition, water elimination will take place. So water elimination took place, and you will get this dehydrated product. So alpha beta unsaturated carbonyl compound, right? Alpha beta unsaturated carbonyl compound. So this is the aldol reaction. Okay, so already we have discussed the 1,4 addition or Michael addition reaction followed by aldol reaction is also known as Robinson annulation reaction. Okay, so it is one type of cascade reaction or tandem reaction. Okay, so this Robinson annulation mean, see, in starting metal you have only one ring, and after this tandem reaction you have two rings. So one ring is forming in this in this reaction. Okay, so that is why it is called annulation reaction, and also more specifically Robinson annulation reaction, because Michael addition reaction followed by aldol reaction is taking place. So that is why it is called Robinson annulation reaction. So after formation of this alpha beta unsaturated compound, so what is the next? Next is we have to protect this this carbonyl compound. Okay, this carbonyl compound we have to protect. So we can protect by using this ethylene glycol, right? So ethylene glycol is this one, 1,2-diol, 1,2-diol, also known as the ethylene diol. So after formation of this 1,2-diol, this protection of this carbonyl compound with in presence of catalytic amount of paratoluene sulfonic acid. Okay, so paratoluene sulfonic acid already you know. So this is the benzene ring. Sorry for poor drawing. So this is the SO2H, SO3H methyl. Okay, so paratoluene sulfonic acid, the pK value of this. So this is high. This is also acidic in nature. So you can see the pK value is minus 2.8. So in presence of catalytic amount of this paratoluene sulfonic acid and ethylene glycol, So this protection of this carbonyl compound, this 5-member carbonyl compound will take place, and we will get this. Okay, now what is the next is the reduction. So reduction of this alpha beta unsaturated double bond. Okay, so basically batch reduction condition we can utilize. So basically sub single electron donor E minus. So this electron, so this will add to the 1,4 fashion, and it will reduce this 1,4 this olefin, right? So unsaturated olefin, unsaturated ketone, the reduction of this olefin will happen, and you will get this. Okay, so you have, if you have any question you can ask. Do you have any doubt? Do you have any doubt? Okay, if no doubt, I will continue again. Okay, thank you. So I'll continue. So this bars reduction will take place, and it will give this compound, right? So next is we have to reduce this carbonyl compound. Okay, to get this alcohol. So we can use some bulky reagent. Okay, some bulky reagent known as L selectride. So this is the L selectride. Okay, so L selectride, if you see, this is the borohydride reagent, boron based hydride reagent. The counter cation is lithium plus, and this boron, the side chain is having secondary butyl group. Okay, so three secondary butyl groups are attached to boron, so that makes this hydride reagent bulky. Okay, so due to its bulky nature, it can stereoselectively reduce this carbonyl group. Okay, so you will get only one stereoisomer. So major isomer, so this is the beta hydroxy groups. Okay, so due to the bulky nature of this hydride reagent, so you will get stereoselective reduction of carbonyl compound. So after getting this beta hydroxy group, so we next, in order to get our target molecule, we have to deprotect this ethylene glycol, deprotect this carbonyl compound. Okay, so if you treat with H3O plus, you can easily get this deprotected product. So and this was your target molecule, right? So if you remember, this was our target molecule. Now how we can, so how easily we get this target molecule from this 1,3 diketone compound, right? Now coming to the next problem, if we see this molecule. Okay, so this molecule, if we see what are the, yeah, what are the functional group it is having? The cyano group it is having, ester group it is having, also it is having this alpha beta unsaturated ester, right? Alpha beta unsaturated ester. So how we can get? So basically this is beta alpha beta unsaturated ester, right? So we can think about this CC1 disconnection. So basically the condensation reaction between this carbon and this carbonyl group, right? If we think condensation reaction, so we can get easily this compound, right? So this reaction is known as Novenagel condensation reaction. Okay, so condensation reaction between ester and carbonyl group to get this type of compound. Okay, Novenagel condensation reaction. Now this is okay, this is commercially available. Now from where we can get this molecule? Okay, so this molecule we have to do the retrosynthetic analysis. So basically if we do this CC1 disconnection, right? So this will be the 1,3 dicarbonyl compounds like this. So this is highly acidic proton it is having. You can easily generate this methyl, and if we take methyl iodide, if we take methyl iodide, so this nucleophile will adds here, and you can easily get this compound, right? And this compound how we can get? So this compound we can get from this cyclohexanone, right? So so we will see the forward synthesis how we can generate this beta sorry alpha beta keto ester from this carbonyl compound from this cyclohexanone, right? So this is the starting material. So if you treat with sodium methoxide, okay, so sodium methoxide it will take abstract proton from alpha side, and then this carbon and will add to this scent carbonyl carbon. Okay, so this is the ethyl. So this is a known compound, diethyl carbonate. Okay, so diethyl carbonate. So this will take place, and you will generate this alpha beta. So this is a beta keto ester, right? So beta keto ester from here, from this way also we can generate. Now if you remember carefully, also we have discussed how we can get beta keto ester from another different way. So we have talked about sorry, I forgot the name reaction. We have talked about I will show you the name reaction. So this is the name reaction, right? Dickman condensation reaction. Okay, so Dickman condensation reaction, from here also you can easily generate beta keto ester, right? So there are many alternatives of alpha beta to generate beta keto ester. So like here we are generating via Dickman condensation reaction, but in our current problem we will generate the beta keto ester. Will generate the beta keto ester via this approach, right? So we have this carbonyl cyclohexanone. If we treat this with sodium methoxide and treat with diethyl carbonate, we can easily generate beta keto ester, right? So sorry alpha and beta, okay, beta keto ester. So Dickman condensation also we can apply. So that time we have to think about this cc1 disconnection. Okay, if we think about Dickman condensation, that time we have to think about this cc1 disconnection. Okay, now we are having this cyclohexanone. Now we did this reaction. Now next is again treatment of this dicarbonyl compound with K2CO3. So this will we are having this another CH acidic proton. It will take this proton and adds to this methyl iodide. Okay, so we can easily generate this compound, right? After getting this compound, we have to do some unknown reaction known as Novenagel condensation reaction. Okay, basically diethylamine. So this enolate will form here first. Okay, so this enolate will form first, and it will adds to this carbonyl carbon. Okay, and it will give this beta hydroxy. So this is alpha beta, right? So beta hydroxy ester, and you will get beta hydroxy ester, and in heating condition you will get the elimination, okay, elimination of water, and you will get this alpha beta unsaturated ester. So the name reaction is known as Novenagel condensation reaction. Okay, so Novenagel condensation reaction I have discussed about Doebner condensation reaction in a previous slide, previous I think 3 4 slides, and slide number 3 and 4. So in Doebner condensation reaction, we use acid, but in Novenagel condensation reaction, we have to use ester. Okay, so this mechanism is almost same. So I am not going to the details about Novenagel condensation reaction mechanism. You can easily search in Google and you will get the mechanism. Okay, so this is our target molecule. This was our target molecule, and we could synthesize this target molecule from cyclohexanone, right? Now the last example of this today's tutorials. So how we can synthesize this molecule? Okay, so this molecule, if you see, it is having this four member ring with this substituents OBN and amine. So how we can think the disconnection approach? So we can easily get this amine from acid, carboxylic acid. So functional group, but with the help of FGI or functional group interconversion, right? So this acid how we can get? So acid we can get from this dias diester, okay, 1,3 diester. And this ester diester how we can get? So basically diester it is having two acidic proton, right? And if we take treat with this treat this compound with base, two equivalent of base, and it will acts as a nucleophile and it will adds to this electrophile, right? Two times it will act to this electrophile, and you will get this one, two, three, and four member ring, right? So one, two, three, and this four number four carbon. So it will generate this four member cyclic compound, right? So now in forward synthesis, how we can start? So we have to start from here, and if we treat with sodium ethoxide, the pK value of this diester 1,3 diester is around 13. Okay, so the pK value, this is the pK value. So pK value you should know for acidic compound, and sodium ethoxide is around 16. So the pK value, this compound active methyl compound is 13 and the sodium ethoxide is around 16. So first this will take proton from here and it will add here. Similarly another equivalent of base will generate enolate here and it will add to this electrophile, and you will get this four member ring, right? Now if you are having this diester 1,3 diester, if you do the ester hydrolysis in presence of KOs and water by heating the reaction mixture, you can get the ester hydrolysis to get this acid, right? Dicarboxylic acid. Now what next? We need one carboxylic acid at this center. So basically we have to do, in order to get one carboxylic acid at the center, we have to do decarboxylation, right? So decarboxylation how we can get? So basically if we treat this compound with mineral acid HCl and then two reflux, okay, so we can get the decarboxylation of one of the carboxylic acid, okay, so minus CO2, removal of carbon dioxide. In presence of mineral acid in heating condition we can get this carboxylic acid, right? Now if we treat this compound with SOCl2, right, so we can easily get this acid chloride, okay, so carboxylic acid to acid chloride by treatment with SOCl2 we can easily get. Now we have to install amine here at this center in presence of instead of carboxylic acid we have one NH2 here, okay, so how we can get? So basically first we have to do this acid chloride to sodium azide, okay, so carboxylic azide, okay, by treatment with sodium azide. So sodium azide is a salt. By treatment with sodium azide we can easily get this CON3, right? Now if we heat this reaction, so what we will get after treating with sodium azide, and if we heat this reaction we will get this isocyanate, okay, by Curtius rearrangement. So all of us we know the mechanism of Curtius rearrangement. I am not going to detail of Curtius rearrangement mechanism. So basically, if you have this azide CON3, if you heat this reaction mixture, you will get this isocyanate intermediate. Now this water treatment of water, it will add to this carbonyl carbon, and you will get finally you will get this amine, okay. So this was our target molecule, right? So in forward in retrosynthesis this was our target molecule, and we can see how we can get this target molecule from these two commercially available materials, okay. So this is our last problem for today. So if you have any doubts you can ask right now, or if you have any doubts regarding previous classes, you can ask now also. Okay, I guess you have get an idea about retrosynthetic analysis and forward synthesis. So in coming weeks you will get more examples, and you will get more experience. Okay, so if you have any doubts, you can clearly ask now. Do you have any doubts? Can you please tell? Or you don't have any doubts? You can clearly tell. Okay, I guess you have no doubts. So that is good sign. You understood everything. So thank you. So now coming to this again, I have uploaded the last week's recorded videos into this YouTube channel known as Anirban Mighty. So this is my YouTube channel as guided by PMRF NPTEL administration. So I have uploaded all the recorded videos of each tutorials in this YouTube channel, so you can easily get access to the recorded videos of this tutorials. Also, you can share this links of these recorded videos to your friends who is pursuing MSc or BSc in organic, or who wants to do a PhD in organic. You can share this YouTube link with them. So it's always good to share the knowledge with with your friends, right? So that is how we will end today. So thank you again for your kind attention, and I hope next week also you will join with same energy, and we will continue and we will see other examples, right? So